Welcome to springlib.
Consider two long, straight conducting wires with a linear mass density of lambda, which are suspended from a cord here. So they are attached to a cord and suspended, so that they are each other horizontal and parallel to each other at a distance of d from here to here, distance apart. The two chords are connected to a capacitor with a capacitance of a C with initial charge of a Q0 on the positive plate and a negative Q0 on the negative plate. The current flows, so they are connected to the capacitor here. So this is a positive and this is a negative. The current flows so here in this direction I. So here it flows in this negative direction to a negative chord here. The current flows in opposite direction, so the two chords will repel each other. So because the current moving in opposite direction, they will exert a force on each other and repel, causing them to accelerate horizontally. The magnetic field per unit length is then given by, magnetic force per unit length is given by force per unit length is mu naught times I square 2 pi times the distance between the wires. The acceleration equals to the force divided by the mass, so we can write A will be F divided by M, or F over L will be equal to MA divided by L. Over the short discharge time, the current is not constant, so we take the RMS current instead of the initial. So I will be equal to I naught over square root of 2, where I naught is the initial current. We substitute these values for the first equation that we wrote. Let's say this is our equation 1. We substitute these values in equation 1. So force over per unit length will be mu naught times I square over 2 pi d, which is equal to substituting the value for I, mu naught divided by 2 pi d, I naught over square root of 2 square. The initial current is I naught is equal to V divided by R, where R is the total resistance of the circuit, V is the potential difference across the capacitor, and this gives us V is equal to Q naught times C. Part B of the problem, we substitute the values in the equation that we wrote earlier for this equation. Let's call this equation number 3. So we substitute into 3 and get a force in terms of a potential, force per unit length in terms of potential, which is mu naught over 4 pi d times V over R square. This is equal to, substituting V in terms of Q naught, mu naught over 4 pi d Q naught divided by RC square. We now combine this equation with the equation that we wrote earlier for force per unit area, which is equal to mass times A divided by L. We combine with that equation, taking into account of the density. We know density is density of charge is mass per unit length. So mass over length A is equal to density times A, which is mu naught over 4 pi d times Q naught over RC square. From here, acceleration will be mu naught Q naught square divided by 4 pi lambda R square C square d. Since the initial velocity is 0, then the initial velocity equals the acceleration multiplied with the time constant, which is t is equal to RC. So V naught is equal to AT, that is equal to ARC. Then we can write V naught, substituting the value for the A. So we get a mu naught times q naught square divided by 4 pi lambda rc times d. For part B, we need to find the h that will each wire rise or as a result of the current connection. From the conservation of the equation, we can write 1 over 2 m v naught square is equal to mgh. From here, h will be equal to v naught square divided by 2g, that is 1 over 2g times mu naught q naught square divided by 4 pi lambda rc d whole square. From here, h will be equal to 1 over 2g mu naught q naught square 4 pi lambda rc times d whole square. So this will be the height of the wire.